So now we will see that how to delete an element in a AVL tree. So the algorithm is this, that we will assume that W is the node that is to be deleted. So we'll perform a normal deletion for this W like we did for a binary search tree. Then starting from W, we will travel up and we will find the first node Z such that this Z is unbalanced. Then suppose that Y is the child of Z with higher height, and suppose that X is the child of Y with higher height. Note that in this case the Z, Y and X are not similar to what they were in the insertion. So now rebalance the tree by performing appropriate rotations on the subtree rooted at Z. And again there can be 4 possible cases that needs to be handled, as the X, Y and Z can be arranged in 4 ways. So the first case that I am assuming is that Y is the left child of Z and X is the left child of Y. So we are assuming that the element was deleted from H4, and it couldn't, and that is the only case, because if it was deleted from H4, then only Y could have been the higher height child, because the Y is the child with higher height and the element was deleted from H4. That is the only case that is possible, because we are deleting the element, so that increases the height of T4. So that obviously means that the higher height can only be on the Y subtree rooted at Y. So we are assuming that the height of T4 was changed. T4 was changed from H to H minus 1, and it was definitely changed, because if it was not changed, then Z would not become unbalanced, but Z is unbalanced in this case. And then the Y height is H plus 1. This is the only case, because it is the child with the higher height. It cannot be H, because if Y was H, then the Z will still be balanced. So Y is H plus 1, and similarly the X would be H, because X is the child with higher height, and T3 could be both H or H minus 1. And then X have 2 children, and the 2 of the subtrees have height H1 or H minus 2. Note that both of these could not have height H minus 2, and at least one of them has height H minus 2. So we will do right rotation on Z, and then the heights of different subtrees and nodes will become this. We will see that Y can have height H plus 1 or H plus 2. If the height of Y is H plus 2, then that is the original height, and the entire tree becomes unbalanced. But if the height of Y is H plus 1, that means the height of Z, which was H plus 2, has now decreased to a height of H plus 1. So this tree rooted at Y has become balanced, but we also need to move up. We now need to see from Y and move up and again find the first unbalanced node. There could also be a case that if we go up from Y, we will reach the root. So if we reach the root, then we terminate the program and we don't do anything else. Other case could be that Y is the left child of Z and X is the right child of Y. And then these are the 4 subtrees. Then we will do firstly left rotation on Y to form tree structure like this, and then we will do right rotation on Z. And similar to above, you can again find the height of all the nodes and all the subtrees, and you can see that why it is the correct algorithm, why it is the correct approach. Again, you need to move up from H and again find the unbalanced node and then do similar operations. So again we have 2 symmetric cases. For the first one, the symmetric case would be Y is the right child of Z and X is the right child of Y, and the other would be Y is the right child of Z and X is the left child of Y. So these can also be solved in a similar fashion. You just need to do symmetric operations that you did earlier.